So in our first question, we are going to solve this using nodal analysis, as it says or asks us to in the question. And it wants us to write three equations in standard form and to not solve. And then they ask specifically to find the three equations at the nodes v1, v2, and v3. And they say that the final equation should only have v1, v2, and v3 as unknowns. So the first thing we'll do is actually mark up this picture. So they want nodal analysis, so we care about currents going into and out of nodes. So we can define for now arbitrarily the direction of currents going into and out of each of these nodes. So the first thing I notice is that V1 is actually a big node. So remember, a node is just a wire. So I can say that there's a current coming out of the 4 ohms, or rather the 4 kilo ohms, and also the 2 kilo ohms. So I'm defining all the directions of these currents, and notice that I have to be consistent. So for example, out of node V2, right there, where it has a current that goes from the left side of the 2 kilo ohm resistor to the right side, that needs to stay consistent. So specifically when I'm looking at node V3, the current with respect to the 2 kilo ohm resistor better still be going to the right. So those are the main things to look for when you're defining the directions of the current. And then for V3, there's this 2 milliamps, so I'll just leave that as is in terms of its direction. And then for this 4 kilo ohm, it continues to go up. So now I'm done writing out or rather defining all the directions of current. So now I'll actually start writing the current equation, or the nodal equation for node V1. So here's V1, and we have this 2 milliamps coming in from this one, and then we have some current coming from the bottom branch or wire. Since we don't know how to characterize that at this time, we'll just call it IC, or IC. Also coming into this node is the current from this 4 kilo ohm resistor, and you can characterize that current as V3 minus V1, which are the two voltages or the nodes that surround this 4 kilo ohm resistor. And then you divide that delta V by the 4 kilo ohms. And then you also have the current coming from this path here, coming through the 1 kilo ohm as well as the 2 kilo ohms. Since this is a series path, you know that the current through both the 1 kilo ohm and the 2 kilo ohm is the same. So you can think of this 2 kilo ohm and 1 kilo ohm as one big resistor. And so you can characterize the current going through that as 4 volts, which is coming from there, minus V1, which is the node at the other side of this resistor, and then you divide it by that resistance value, which in this case would come out to 3 kilo ohms. And since now we've captured all of the currents going into the node, there's no currents coming out of the node, so we set that equal to 0. And now for V2, we have coming into the node the current through this 3 kilo ohm resistor, and so you can characterize that as 0 minus V2, where 0 is this ground voltage here, and then you divide that, of course, by the value of the resistance, and then that's all. The only current that's going into the node. And now you have two currents coming out of the node. One of them is IC, and then the other one goes through that 2 kilo ohm resistor, which you can characterize as V2 minus V3 over the 2 kilo ohms. So now you've got two of the circuit equations. The third one is just as simple. So coming into the node, you have the current traveling left to right across the 2 kilo ohm resistor, which you continue to characterize as V2 minus V3 over the 2 kilo ohms. And also coming into that node is the 2 milliamps. Coming out of that node is the current that goes through the 4 kilo ohm resistor from bottom to top. And so you can characterize that as V3 minus V1, which are the two voltages that surround that resistor. And then you have the 4 kilo ohm resistor itself. So now we have three equations and 4 unknowns. So the fourth unknown in this case is this IC. So we need to figure out what to use for IC. So IC, we said, is the current through this voltage-dependent voltage source, and we said that we couldn't characterize it. Normally, the way we would do it is using Ohm's law, but since there's no resistance that's obvious to us across nodes V1 and V2, we can't use Ohm's law to help us. But ultimately, if we look back at the hint in the problem, it tells you that there's a supernode in this question, in this circuit, so you can use that to your advantage. And the supernode is exactly what we were just looking at. It's this right here. This actually gives us a fourth and final equation. And so if we look at this circuit, specifically at the supernode, this is saying that V1, that voltage, is greater than V2 by an amount 2Vx. So we can write that out as our fourth equation. So our supernode equation says that, again, V1 is equal to V2 plus 2Vx. There's V1, and that's equal to V2 plus 2Vx. So now we have 4 equations and 5 unknowns. So that fifth unknown came from this Vx. So we need another equation. And so if we look here, we have to figure out what Vx is. And if we look at this picture, Vx is defined as the voltage across this 3 kilo ohm resistor. Well, V2 is defined the exact same way. Remember that if you just see a node called V2, that node has a voltage V2 with respect to ground. Therefore, we have another equation which tells us that V2 is equal to Vx. So V2 is equal to Vx. At this point, we have a total of 5 equations and 5 unknowns, and so we have everything we need in order to solve this circuit. So the way I would approach this during an exam, I might leave this toward the end and then move on to the other questions so I can get all the work out of the way first. Because at this point, it's just algebra if you really want to simplify these equations into the standard form as they ask you for.